Prop-2-ene-1-ol is a natural chemical found in garlic. It is also used in the production of plasticizers. Prop-2-ene-1-ol can be prepared by reacting 3-chloroprop-1-ene. Okay, so this is our structure, and then it says we could make it from 3-chloroprop-1-ene, like that, with dilute aqueous sodium hydroxide. Name the mechanism. Well, we're swapping the Cl for the OH, and the Cl minus would be an electron pair donor, so it's nucleophilic substitution. Prop-2-ene-1-ol can also be formed from this diol, propan-1,3-diol, in the presence of an acid catalyst. Name and outline this mechanism. Well, we can see that we're losing this OH here, and we're also losing a hydrogen from a neighbouring. So this is an elimination mechanism. We're losing things, losing water. And then it says outline that mechanism. So we're trying to lose this OH group and then this neighbouring hydrogen, but we're not trying to lose this second OH group. So what's going to happen is it's an acid catalyst. It says it's an acid catalyst. So these electrons on this oxygen are going to pick up the proton from the acid. We're going to protonate the oxygen. That will help it be a better leaving group. It's going to become a water. It becomes positive because it gave away electrons. So at this point, we're just redrawing out the molecule. So we're going to lose this protonated hydroxide group. That will give us a carbocation. Because we've lost something from that carbon. And then remember, this second hydrogen is going to be lost to form the double bond between carbon number 1 and 2. So we've now got 2 hydrogens on carbon number 1 and a hydrogen, and then a CH2OH on our remaining carbon. Prop-2-ene-1-ol forms an addition polymer. So remembering that our structure had a double bond, and then a H, and then a CH2OH. So this is our kind of like starfish shape. And what we're going to do is we're going to make that starfish stretch up. So we're going to break the double bond, and we're going to make that starfish stretch up and down. It's doing a big stretch. So the hydrogens are going up, and then this hydrogen is going down, and then the CH2OH, and then it's going to join to many others. It's a repeating unit. Figure 3 shows the infrared spectrum of a functional group isomer. So it's not prop-2-ene-1-ol, it has a different functional group. That could be that instead of the ene, it is an ane, or instead of the ol, it is something else with an oxygen, but it's not an ol, so like a ketone or an aldehyde. This isomer reacts with acidified potassium dichromate, which means it's either a primary alcohol, a secondary alcohol, or an aldehyde, because they're the things that can be oxidized by acidified potassium dichromate. It says draw the structure of the isomer. So with infrared, we know that anything below 1500 is the fingerprint region, so we can ignore that when analysing. We can see here that we've got lots of CH. What we don't have here is an alcohol group that would look like this. So we don't have an alcohol. So that means we can get rid of primary or secondary alcohol. We know we've got an aldehyde. And what we know here is that this peak at 1700, just over 1700, is a C double bond O peak. So we know we need a C double bond O. We know it has to be an aldehyde and not a ketone. We know we've only got 3 carbons. Aldehydes have to be on the end. And we know in total that we have got all the same atoms, which was C3, because it's an isomer, H, 1, 2, 3, 4, 5, 6, and an oxygen. So 3 carbons, 1 oxygen, 6 hydrogens. It's going to be propanal.